All right, so now we're going to page 4 in the lab manual. Let me just again reiterate. If you're feeling a little bit overwhelmed at this point, don't let that one throw you, because remember, what we've done is we've taken a walk up to the finish line of the course. And so you're not expected to know about all of these concepts that we've been discussing thus far, but rather to survey the landscape at that finish line and see what it is that we're going to have to tackle over the next 14, 15 weeks or so. So again, just be of good cheer. You're not expected to know about all of this, but nevertheless, let's press on. So now we're on page 4, and right at the top of page 4 it says, so what is dark matter and what do we know about it? And right below that there's a typo where it says number 8. That's supposed to be number 1. So just kind of to recap here, number 1, the laws of motion. Let's just talk briefly again about the laws of motion, given to us by Johannes Kepler and Sir Isaac Newton. They are well proven and reliable. And they are predictors. They are predictors of orbital behavior. Yeah, they're pretty much done deal. I mean, this is how NASA put satellites into orbit. This is how NASA put men on the moon. So this is done deal stuff, okay? And if we accept that, then the only reasonable explanation of measured discrepancies is undetected or missing mass, like I showed you with that formula. So the only reasonable explanation So there it is. The only reasonable explanation of measured mass discrepancies is undetected or missing mass itself. All right, this is how science works, and that's another topic that we're going to touch upon probably on a weekly basis. We want you to come away from this with an understanding of how science itself works. So more on that as we move along. All right, so we got that. Now, what else do we know or not know? Well, we know this. We know that whatever this stuff is, it does not emit photons in any frequency or wavelength. Does not emit photons in any frequency or wavelength. We have the means to detect if it's there, and it's not there. Number three, it does not interact with normal matter. Okay, that's, when we say normal matter, that's the stuff that makes up us, atoms and molecules. And when we say it does not interact, we're talking about it on a chemical basis, among others. So, in other words, H2O, that's water, you know, two hydrogen atoms, one oxygen atom, presto, you got a water molecule. There is no unknown, heretofore unidentified piece of something that has been discovered in any of these chemical compounds. There's no mysterious piece of a molecule that has been discovered that, you know, might be dark matter. It doesn't work that way. So this comes right down to basic chemistry. So no chemistry has been detected or observed. Okay, so that's what we know so far. I'll give you a minute to write that down, then I'm going to clear the board. You can hit pause if you need a few minutes. So here we go. Number 4. It does not interact with photons. Now, we talked about photons in the previous discussion. That would be one type of an interaction. And it would also have to do with something called the photoelectric effect. Which is a phenomenon that Einstein studied in depth, and that's what he actually did get his Nobel for. Okay. There's no candidate. There is no candidate within the standard model of elementary particles. Now, when we talk about elementary particles, what we're talking about are the pieces and parts of atoms. So what we're talking about here are, for instance, for example, quarks, leptons, bosons, etc. Okay. Pieces and parts of atoms that we know exist, none of them fit the bill for being dark matter. It just doesn't work. Okay. So by the late 1990s, it was thought to make up 90% of the universe. Okay. Now that would seem to run into opposition with what we talked about right at the outset in terms of what percentage of the universe dark matter makes up. 23%. Well, where's this coming from? Well, this is before we had even thought about the existence of dark energy. So our awareness of dark matter precedes our awareness of dark energy. So we're talking about our view of the universe as it stood in the 1990s. So now, number 7, Rubin's calculations coincide with this 90% figure. And again, not counting dark energy. Number 8. These calculations also inferred the size of a halo of dark matter surrounding galaxies and galaxy clusters. Now, one other thing before I erase this, when we talk about dark energy, when we say that dark energy is roughly 73% of the universe, dark matter 23% of the universe, normal matter 4% of the universe, this goes to in large part the most famous equation in the world. There it is, E equals mc squared. What's that saying? Well, you can read it left to right, or another way you can read that is you could say that there is an equivalence that exists between energy and mass with a conversion factor of the square of the speed of light. We'll talk about that a little bit more down the road also. But it also tells us, and this is the important takeaway at this point, it tells us that mass and energy are two sides of the same coin, just like space and time are two sides of the same coin. So this is where this dark energy piece comes in as well. All right, so we're talking about a halo of dark matter surrounding galaxies and galaxy clusters. I'm going to erase this and do my best to sketch this one out for you before we go to the next page. I usually have more success doing this on a chalkboard, simply because chalk lends itself better to this sort of a sketch, but I'll try. see what I can do with markers. All right, so let's say that we're looking at a spiral galaxy edge on. All right, and so they kind of bulge up toward the center. All right. All right, so here's the spiral galaxy. And what they're saying is surrounding this galaxy, what they're able to infer, and let's be clear about this word infer. I know that one throws a lot of folks off. If I imply something, you infer its meaning. So we can infer that there is a big glob or a halo of dark matter surrounding something as large as a galaxy, kind of like this. And again, we're able to measure this using the methods that we've discussed thus far. And again, remember the 3 lines of evidence. Rotational velocities of galaxies, orbital velocities of galaxy clusters, so there's 1 line of evidence. Gravitational lensing, the 2nd line of evidence. 3rd line of evidence is temperatures in the intercluster medium. So we can measure all of these things, and we seem to be able to infer from all that galaxies and galaxy clusters are surrounded by this halo or glob of dark matter. Again, what it is, we don't know. We just know it's there. All right. Page 5. Yes, page 5. Okay, so what are the possibilities that we have looked at? And we've looked at a number of them and ruled some out, and it's important to understand what they are and how we did rule them out. So the first, we have 2 categories called machos and wimps. I didn't make that up, that's what they are called. Who said, never let it be said that astronomers and cosmologists do not have a sense of whimsy. So what are machos? Well, they are massive compact halo objects. Okay, they were hypothesized. It's important to understand the language of science, not theorized, hypothesized. Okay, so what were they supposed to have? Well, for these things to work, they had to have high mass, they had to emit little or no light, and they had to be present throughout the galaxy. Okay. All right. For these things to work, this is what they had to have. All right, so what were we looking at? Well, the possible candidates were black holes, brown dwarfs, that's a type of star, or neutron stars. Okay. Now, the pros. they can cause lensing, and they are dark. Okay. Cons, which pretty much threw them out of the running. There just ain't enough of them. Yeah, that's it. Just not enough of them to account for it. Okay. So we looked at machos, massive compact halo objects. Nope, doesn't work. Not enough. Okay, so then we looked at WIMPs. What are WIMPs? WIMPs are weakly interactive massive particles. Okay. The first candidate that we looked at was a neutrino. We thought maybe that was the guy. Some things that we thought might make it a good candidate. Well, it does interact with gravity and the weak force. And it was an early suspect, but it was ruled out. Because, again, just not enough of them. Okay. Now, this weak force, gravity and the weak force, we're going to come back to that in a couple minutes here. So just hold on and we'll talk about that. Okay, so what's left? We call them, at present, we call these exotic particles. Okay, what are exotic particles? Well, they're hypothetic particles and they are predicted by a branch of physics called supersymmetry. High mass, which makes sense. Invisible to all wavelengths of light. And the search is ongoing. In underground detectors, and at I'm getting ahead of myself. In underground detectors, and they're underground to avoid cosmic rays. What are cosmic rays? Well, that's stuff that comes in from outer space, and it's just a general term for all the garbage that gets thrown our way, and it can be anything from individual nuclei from atoms to different types of light wavelengths. It's but cosmic rays. You have cosmic rays going through you right now. Neutrinos are going through you right now. They don't hurt you for the most part. And the other place that they're looking at them, looking for it, is in the Large Hadron Collider. That's at CERN. Okay. So they're taking this pretty seriously. Now, this idea of hypothetical particles being predicted by a theory in physics, this is nothing new, especially in the 20th century. Quantum physics is arguably the most successful theory in physics ever. And it begins, the ideas in quantum physics almost always begin mathematically. An example of a prediction by quantum physics is the cell phone or the smartphone that most people have. And you have a touch screen on that phone. That touch screen works because of something called tunneling. Tunneling was something predicted by quantum physics some years ago. And so there's an example of how successful this is. Another example would be, some of you may have heard of this, the Higgs boson, otherwise known as the God particle. The Higgs boson is a subatomic particle that was predicted by a physicist by the name of Peter Higgs back in the 1970s. And it was only roughly 10 years ago that our technology got to a point where we were able to actually detect one. And that was done at the Large Hadron Collider in CERN. Quite frankly, we didn't have an atom smasher powerful enough to uncork one of these guys so that we could see it. And so this is how this stuff works. And so it may very well be that we will ultimately detect one of these particles. We don't know yet. But folks a lot smarter than me seem to think so. These are the folks whose first names are Doctor and last names are PhD. And so they're putting a lot of time, effort, and money into this type of research. Now, I wanted to talk also about this idea of weak force. Now, you got some space at the bottom of your page. And I want to talk just briefly about the 4 fundamental forces in the universe. Now, when we talk about force in the terms of physics, what we mean by a force is a push or a pull. That's how Sir Isaac Newton defined it. And I'm going to add my own definition to that. A force is that which may affect motion. And the 4 basic forces in this universe, everything else is just a variation on a theme. They are G, which is gravity. Strong force, or the strong nuclear force. the weak force, the weak nuclear force. And electromagnetism. All right. So gravity we've talked about, and we're going to talk about extensively. Gravity, believe it or not, is the weakest of the four forces. It is. The strong nuclear force is the force that holds atoms together. That kind of makes sense. The weak nuclear force is the force that is associated with radioactivity or radioactive decay. And electromagnetism, that's photons. That's anything from light to radio waves to X-rays. But those are the big four, okay? And if you're going to do astronomy and cosmology, you should know these. And I might ask you again under more formal circumstances. So yeah, know what the four fundamental forces in the universe are. I will also tell you that gravity is described by special relativity. I'm sorry, general relativity. I misspoke. And these three forces are described by quantum physics. And the 800-pound gorilla in the room is the fact that we cannot reconcile these two different theories, even though individually these theories work out beautifully. General relativity is to date the greatest, most effective, most comprehensive description of how gravity works that we have thus far. And quantum physics describes these three forces also beautifully. But there's still a conundrum to be solved between the two. But that's for another discussion. But for the time being, just know what these four are. Gravity, strong force, weak force, electromagnetism. Make them part of your vocabulary. Now, on the next page, you'll see there's a synopsis for dark energy, and that's for you to read on your own, but find a spot. I'm going to ask you to find a spot on the left-hand side of your book where you've got some blank page. I just want to throw one other idea out there. As you saw in the film, we have discovered that, well, we know that the universe is expanding. And up until recently, there were two possible scenarios that we were looking at in terms of what the fate of the universe was. One scenario was that the universe would continue to expand, but because of the gravitational attraction between everything in the universe, clusters of galaxies, and now dark matter, that it would slow down and slow down and slow down, but never quite get to a stop, but it would just continue to slow, still expanding. Another scenario was that it would slow down, and because of gravitational attraction, come to a stop, and then begin to contract and come to what would be called the Big Crunch. Well, that all went out the window because we observed a standard candle in a very distant galaxy. A standard candle that we used was called a Type 1a supernova. Now, a Type 1a supernova, we're going to talk about that in greater depth. But a Type 1a supernova is a very, very, very precise standard candle that we use to measure distances. We observed this Type 1a supernova in a very, very, very distant galaxy. And what we were surprised to see was that galaxy was moving faster away from us than it should have been, much faster. And the upshot of it is we've done subsequent measurements of other distant type 1a supernovae and measured the rate at which the galaxies that they are contained in are moving away from us. And surprise, surprise, it turns out that roughly 5 billion years ago, the universe began accelerating in its expansion. The universe being roughly 14 billion years old, so we're saying that 5 billion years ago, that rate of expansion stopped slowing down. In fact, it began to accelerate. A way to think about it would be like this. Imagine a roller coaster ride, and here you've got a roller coaster car that you've pushed up the hill. Now, if you've pushed it up and it's just being carried along by its own momentum, it's going to get slower and slower and slower. But if you push it hard enough so that it gets here, reaches the crest, it's going to go down the other side, and what's going to happen? Its speed is going to increase. And that's kind of what has happened here. So here's the moment of the Big Bang. Here's present day. So this is time 0. Here's present day. So that would be right about, here's the beginning of the universe, the Big Bang, right about at the 9 billion year point, 5 billion years ago, evidently the universe hit the crest and started accelerating in its expansion. Now, what is this stuff? Again, we don't know. We use dark energy for just kind of a placeholder term. Who knows? It may even be a fifth force. There are some physicists who are wondering exactly that. But we're still trying to figure that one out too. This is recent discovery. This is stuff that has come into light within your lifetime. We're living in an incredible age of discovery in astronomy and cosmology. And so that's the basic idea behind this dark energy. When we use the word energy, let me just go back to Newton's idea of energy and how he defined it. Newton defined energy as the ability to do work. Well, what did he mean by work? Well, work is an applied force times a certain distance. So if I applied a force of, say, on a box, let's say I applied 10 pounds of force on a box and pushed it along 5 feet, I would have accomplished 10 times 5, 50 foot-pounds of work, which required 50 foot-pounds of energy to accomplish. So that's what we mean by energy. So is something being moved here? Oh yeah, absolutely. Remember how we define force, that which may cause motion. Okay, what's energy? The ability to do work. Okay, so this is where the terminology comes in. So something's going on here. Something is pushing the universe out faster than we had ever expected it to be. It's not coasting. We know that the universe is not coasting. It's not slowing down. It's not coasting to a stop. It's actually accelerating. That requires energy. That's the important takeaway here. In order for it to increase in its rate of expansion, that requires energy. Otherwise, everything we know about physics is wrong. So there has to be some type of energy that is accelerating, speeding up this expansion. And again, it's recent stuff. We don't know what it is. We just know what's happening. So that covers, that's our recap of dark matter and dark energy. All right, and we'll go on to other topics here very soon. Yeah, we'll stop right here.